So go ahead and get this started. All right, thanks for showing up, all you wonderful people. You make it a little bit more bearable when I can rely on you guys,
Okay.
the ones to take care of these uh, lessons and everything else like that. So let's go ahead and get started with what we have today. I'm going to, oh, there it is. It's on the last one. Oh no, I forgot to clear it off from the last class. That's just how busy I was all day today. So let me go ahead and just tidy this up and we can go over it together. Yeah, it's just been a really crazy morning this morning, and I even ate lunch here just because it was so crazy, and I'm still behind. All right, so here we go. We're gonna finish, we're gonna start complex numbers, which is just another way of saying imaginary numbers. So what we're going to do today is we are going to simplify and try to understand complex numbers. But this is really more of the intro. There's going to be another lesson next week on simplifying complex numbers. So let's just get into it. But before that, let's go ahead and we'll take some time and look at some memes. Memes are good for your mental health. Well, at least I like to think so. Okay, the number I. When you're working on algebraic equations, just algebra equations in general, usually we don't see the letter I all that much because it's actually a specially set aside variable that we almost never use. You use A, B, N, X, Y most often. Sometimes you'll have some different variables in there, but the one that you almost never see is I. And again, I is a special variable that we set aside just to show that something is an imaginary number. So I'm going to ask you to try and imagine a number. And let's see if you can do that. So I want to look at the square root of negative 100. What would that be? Now we know what a number like, say, for instance, the square root of 9 is. That's easy. Because remember, when you're looking for the square root of 9, you are looking for two numbers that you would multiply to get 9. In this case, it's 3 times 3. When you take it out of the radical, there's only 1 3 there, because each of those 3's is half power. But if we have a negative number, which is what it says here, I is equal to the square root of negative 1. So how do we take care of negative 1 in a square root? Well, okay, so if I ask this to students in the class, usually they will say, well, wouldn't it be 10? Because 10 times 10 is 100. But remember, we're trying to get negative 100, not 100. So the other response, they'll be like, oh, okay, well, how about negative 100? And we try that. So negative times a negative is still going to be a positive. And then they say, okay, well, I know what to do. We could go with negative 10 times positive 10. How about that? Now that does work out, but the problem is you got to remember that a square root is the opposite of a square. So I cannot have two different numbers. I only have two choices. I can either take negative 10 and square it, or 10 squared. I cannot choose two different numbers for that square. So that's where we run into the problem, is that we cannot pick two of the same number to multiply together and get negative 100. It just doesn't happen. Hopefully you're taking notes on this. I think this one's going to come back in a bit. But for this lesson, you will need these as reference for the work. So if you don't have them, the work's going to be a lot more difficult. You could probably find resources elsewhere on some of this stuff. I think some other students may be doing something like that. But anyway, we also have another one. We have I squared. So we have our imaginary number, which again is equal to negative root 1. And if I have I square, remember that means negative 1, the square root of negative 1, and square it. So I multiply 2 of them. And you may remember from solving radical equations, these two operations are inverse operations, meaning they are opposite and they will cancel each other out. So root and square root cancel each other out so that I'm only left with negative 1, and that's how we get negative 1, like that. Now there are 4 more of them, but I put it in a nice list format for us to work with. So this next slide, you are going to need to copy this down, and you do have a few options. The options you have is, if you're writing notes, okay, start writing it now because there's going to be a lot of stuff on here. But since this is a video, you can also do a screenshot if you know how to do a screenshot. It's different on almost every computer. On my computer, there's 1 button that you push for screenshot. Some of them may require 2 buttons, like this FN button over by your left-hand side. And then you push that down, and there's usually a button in the upper right corner somewhere. For me, it's above the plus sign. But sometimes you gotta push a combination of buttons in order to get a screenshot. Because again, you will need this for the lesson. So this is telling us about the powers of I. So again, I, it means imaginary number. And some modern mathematicians have this problem with imaginary number. And that is that it's not really imaginary. It's actually pretty complicated. It's been explained to me, and maybe I don't fully understand it. There are some good YouTube videos out there that explain why I is sometimes referred to as complex rather than imaginary. But that's also something slightly different as well. So what exactly do we have? Why is imaginary number a thing? Why do we even bother with it? So again, I'm giving people time to write these down. So I'll just go on this little story about why we have imaginary numbers. So imagine that you are paying people, a construction team, to build a house. Maybe like a simple hogan, a small wood cottage or something like that. Or in my case, I'm gonna use a small brick house. So you have people who lay bricks. You have maybe a team of people that will dig holes so they can put pipes in. You have some people that hook up the electricity. You have some people that will make interior walls, roofing, framing. Right? You have a lot of different people in those teams. But let's say that you run out of something. So the people who are laying bricks all of a sudden run out of bricks. Okay, well, you have more bricks coming, but they won't be in until tomorrow. So what do you have those guys do? Do they just stand around? No, you could probably have them do something else. You could probably have them, dig the trenches for have them help the plumbers dig the trenches. You could probably have them help out the framers if they can do that. You might have them sort materials. There's a lot of things that you could have them do rather than just stand around because you're paying them by the hour. And that's kind of what imaginary number is like. It's like moving something somewhere else. Now, when we were solving radical equations, you may have noticed that we did have some of these that came out to be negative roots. What we did was we set those aside, we worked around them, and if possible, we brought them back at one of the later steps. So that's what imaginary numbers let us do, is it allows us, if we're like doing a formula or an equation, that we don't have to stop as soon as we run into a negative root. Because again, you have to keep working on the other stuff around it. So that way, as soon as your bricks come back in, then you can start working on them. You can resume right back where you were. So that's kind of why we have imaginary numbers. And we have this chart here. So this chart looks pretty complicated. But it's actually kind of easy once you know what the pattern behind this chart is. So here again, we have the powers of I, so I to the n power, and we increase the power by 1 each time. So I to the 0, I to the 1, I to the 2 power, I to the 3 power, and so on. So we're just using our integers. Well, in this case, we're using whole numbers, but we have what it comes out to be. And this column is important because you will need this one for your answers. Now, some of these are pretty obvious, like if you remember on last week's lesson, when we were introducing exponents, you may remember that one of the properties of exponents is that if they have a 0 power, then they are equal to 1. Any number. If I have 100 to the 0 power, that is going to be 1. It doesn't matter how big it is. Every number has 1 to start with at the 0 power. That's the definition, so that's why it says it over here. So because any number to the 0 power is 1. All right, but here I have I to the 1 power. Now this one's another obvious one because anything to the 1 power is just that same number. Like if I have 5 to the 1 power, it's just going to be 5. Anything to the 1 power is just that number. So I to the 1 power is the same as just I. Now here again, we get into a little bit more complicated stuff. I went on, for this one, I squared, I did kind of explain that on the last one. So I squared equals root negative 1, because that's what I represents. And if I square it, these two things will undo each other, the square and the square root, and that allows the negative 1 to come out. So that's why that is negative 1. For I to the 3 power, that means negative 1, sorry, the root of negative 1 times the root of negative 1 times the root of negative 1. Because again, I'm multiplying it by itself 3 times. And we know that these two become negative 1 times root negative 1. And we know that this is going to be I, so I can take this out and replace it with I, because again, we know that root negative 1 is I times negative 1. So that's just going to be anything times negative 1 is just going to switch the sign. So that's why we have negative I. And for the next one, I have a better example in the exercises, so we'll go ahead and cover that. But again, these are all just the justifications here, like I to the 4 power is I squared times I squared, which if we replace I squared with negative 1 times negative 1 is just going to be 1. Now you'll also notice that this chart doesn't go very far. It only goes to about 5. What happens if you have numbers greater than 5 in the power? So let's look at I to the 6 power. Now, rather than writing all this stuff out every single time, I'm going to tell you a shortcut. So let me show you the shortcut, and that is, let's look at the outcome, the results. I have 1 right here, right? The answer is 1, and then the next one is I. So if I have I to the 6, what's the next number in the pattern? All right, you may not have seen it right away, but it's going to be negative 1 because that's the next number in the pattern. What about I to the 7? If I had I to the 7, what would that next number be? You're starting to see it? Oh, wait, I picked the wrong one. That'd be negative I. There you go. So this pattern repeats itself every 4 numbers. So it's kind of like this one's kind of hard to explain exactly, but it's kind of like a spinner. If you have a spinner, with 4 possible outcomes, it doesn't matter how many times it spins around. What we want to know is where it ends. So again, I'm going to show you a bit of an easier way to do this. But basically, all that's going to happen is that this thing's just going to repeat itself. So let's go ahead and get to some exercises here. So on the first part of the homework, you run into something like this. I don't have the packet in front of me, but it's somewhere near the end. So this top part, maybe, hopefully if you were following along and taking notes, you would already have that top part. But I'm going to go ahead and explain what's in the box, and that is complex numbers. So complex numbers are a combination of a real number and an imaginary number. So we kind of put them in this form of a plus b times I. And it says A and B are real numbers. So in other words, if it's got to be a real number, because if it's not a real number, then it would be an imaginary number. But if you have 2 imaginary numbers, then it becomes a real number. So tricky. But just keep in mind that, again, real part, any number that you can, nearly all the numbers that we've had are real numbers. The imaginary number, again, is something a little bit more difficult to explain, but basically it's just anything that comes out to the square root of -1, or a square root of any number for that matter. And some of them, well, in the next few lessons, we'll go ahead and take the square root of negative other numbers. So this first exercise is pretty easy. I don't expect there to be a whole lot of issues with this one, because again, every number only has 2 parts. So I think the homework for the most part has ones with 2 parts, but I'm going to cover some of them that only have 1 part. So here I have regular number, which is -8 on this first exercise. So I'm going to go ahead and put -8 right there. That's the real part. This imaginary part here, again, is the one that is paired with the variable I. So that would be 7. But remember, everywhere that the number goes, this sign also has to go with it. So in this case, I have -7. And that's pretty much all we do. We don't really need the I part. I mean, I told some of my classes you can go ahead and leave it on. I know what you're talking about. But in this case, we're mainly concerned with the coefficients. Okay, and like I said, that one has 2 parts and they're easy to tell apart from each other, but I picked a few of the examples that have only 1 number. So in this case here, the real number is what I'm looking for. There is no real number. So I'm going to put 0 here, because we could, if we really wanted to, expand it to 0 plus 26i, and the 0 would be the real part. And that would make the imaginary part 26. So there we go. You don't really need both parts. Sometimes you can just, you don't have to write the whole thing out. Like for instance, in this example number 3, I only have, again, 1 part. So one of them is missing. And I have to look at it and say, okay, which one do I have actually? Do I have the real part or do I have the imaginary part? Which in this case, there is no letter I. So that means we are looking at the real part. And 15 is a real number. It has all the properties of a real number. It can be written as a fraction. It can be written as it fits as a natural number or a whole number. So it works out. And then we have B, which we don't have one. And again, I could put 15 plus 0i, which means that there is nothing there. And finally here, we got one more. So in this case, again, we are lacking a real part. I only have one number. And now I have to find out what the imaginary part will be. So what is the number in front of here? All right, so it's going to be 1 because if you don't see a number in front of the variable that we call coefficient, if there is no coefficient, then it's 1. Okay. Because if it was 0, then there wouldn't be anything there. If you ever have a coefficient of 0, that means that it's just, because 0 times anything is going to be 0, meaning that it's just going to fall off. You're not going to have any other numbers. All right, so that was the first part. Let's go ahead and do the next part. This is the part that the main lesson is going to be focused on. And that is evaluating the powers. So I have a lot of different powers. And some of these powers are a little bit different. Some are pretty big, like that one is 259. And some of them are kind of small, like 24 and 16. But again, I'm going to show you an easier part on how to do this, an easier method. Okay, so it would make most sense to start with problem number 1, but in this case, I'm going to start with problem number 3 because, well, it's kind of a smaller number. And I think once you kind of see this a few times, you're going to get the hang of it and you realize it's not all that tough. So here's the thing that we're going to have to do. So again, remember, there are 4 options. So it's like a spinner. And each one, well, if you spin a spinner and there are 4 outcomes, it has to be one of those 4 outcomes. It doesn't matter how many times you spin it. You know, like if you've ever watched a game show like Wheel of Fortune or The Price is Right, where they have to spin that big gigantic wheel while the people say big money, big money. Okay. I don't think modern people now watch game shows, but back in my day, if you were homesick, then you had to watch game shows. That's like the only thing on TV. But anyway, we're going to divide it. I'm going to divide the exponent. I'm going to divide the power. So in this case, my power is 24. And now this is a little bit different because normally when you divide a number, you are looking for how many times it fits in there. But for today, that's not really important. If I asked you, what is 24 divided by 4, and you said 6, that is the right answer. That answers the question. 6 is the quotient of those 2 numbers. But again, this is not what we're looking for today. Because it's like saying you spin the wheel and it goes around 6 times, but we want to know where it landed. We don't want to know how many times the wheel went around the board. So in this case, the thing I need, the most important thing is this part here, the remainder. So right around maybe 4th grade or so, you were working on division. And you notice that not all numbers divide nicely. Sometimes you will get pieces left over that we call the remainder. This is the part we're looking for. Now remember, we want the power. We want to know which power this fits to. And we don't have a chart that goes really high, and we don't really need one. We only need a few of these. So this is I to the 0. That's the new power on this sign. And if I just know what this is, I should be able to get which number it was from the chart. So earlier in the lesson, I told you to write down that chart because you will need it. So in this case, this one I don't really need the chart for because I know that any number to the 0 power is going to be 1. Oops. This is the part that I need right here. The answer is 1. Okay, now that was the easy one. Let's go ahead and do the other two before that and see what happens. So 4 dividing into 73. Now again, actually you don't really need this top number at all. So for some of my morning classes, I wasn't even putting numbers up here. That's not really the important part. But I know for most people, it does help to do the division the way you're used to it. So again, we ask ourselves, how many times does 4 go into 7? Well, it goes in there 1 time. To get the next number, I would have to multiply this times this, our outside number, and that gives us 4. So I'm going to put 4 here, and I'm going to subtract it. And this is the next number. I'm going to bring this number down and treat them like they're together, so that'd be 33. So 4 goes into 33, and again, I don't really have these numbers right off the top of my head, but I know that because they're not really that important. The most important thing, again, is this bottom number here, this remainder. That's what we're looking for. So again, if there was a spinner and you spun it really hard and the spinner went 18 times all the way around and then finally stopped, at this case, it would stop at 1. But that's the important thing. That's the important thing we want, is to know where the spinner stopped. What this means is that we have I, and I divided it, we had 73, and again, that means 73 one-time turns, like 1/4 turns, and this would be I to the 1 power.
Mr. Nance?
Yeah?
Question.
Okay.
You're dividing by 4 simply because you said there's a pattern of every 4?
Yeah.
Okay, all right, thank you.
Yeah, so every 4, it just starts over again. And with this one here, I to the 1 power, you can look at the chart, which if you're not sure, so we can go I to the 1 power here and go back to the chart. And you look at it, I to the 1 power, and we go over to this column here. So in this case, it's just going to be I. Oh, that's a much better way of working this thing. I don't know what I pushed, but now I got a much better view of everything. So any number that it comes up to, now we don't really need to go up to, everything down here is not really that useful, because if you already divide it all the way down, you're only going to end up with either 0, 1, 2, 3 remainder. Those are your only options. So there we go. Our final answer on this is just I. All right, so again, we got it's always by 4. So we don't need to divide by anything else. So 4, and I can't fit it into 2, so 4, I can put it into 25, which again, I know the multiple of 4 before I even know what number it is up here, because again, these numbers up here, they're not important. But again, just stick with your regular division, because you don't want to change things on yourself and confuse yourself or make a mistake or something like that. So bring the 9 down. 4 goes into 19, in this case, 4 times. 4 times 4 is 16. And again, I'm checking for the remainder, because this remainder, since this 259 is the power, I take out 4, take out 4, take out 4, and I do that 64 times until I only have 3 left. From there, I can't take any more out because I don't have enough. So this becomes I to the 3rd power. And again, you can go back to the chart and look at what I to the 3rd power is. Go I to the 3rd power. Look over the next column. In this case, it's going to be negative I. So that's my final answer, is negative I. Okay, just double checking. Now, you don't have to use long division on all of the numbers. In fact, I'm going to kind of show you some different ways to do this. because I think if you see a few different ways, you're kind of like, oh, okay, that makes a little bit more sense. So let's look at 16. Now, if I asked you right off the bat, is 16 divisible by 4? If so, how many remainders is there going to be? And don't forget, you can write it in the chat as well. I had some pretty good participation this morning in the chat box of people. In fact, I had like one kid who was doing it really fast, and either he already knew how to do this, but my guess is he had a calculator somehow, and he figured out a way to make the calculator tell him this. Some people are pretty crafty like that. But again, if I said, okay, well, is 16 divisible by 4? Yes, it is. And that, when you say divisible, that means it fits in there nicely. Because 16 divided by 4 is 4 with no remainders. So that means I have nothing here. And I already have my result of a I to the 0 power right here. So I to the 0 is 1. Oops, I don't need that part. I need just this part. That's our answer there. So some of them are pretty simple. They're not very complicated. Okay, so done with this one. Let's go ahead and go to the next one. And some of these are pretty big, but don't get scared. Alrighty, so let's go ahead and again, we're focusing on the power. So we're taking out sets of 4 until we see how much we have left, which is essentially what dividing really is. When you really break down division, that's really all you're doing is just subtracting that many times. So let's go ahead and go to 543 and see how many times we can divide 4 out of that. So 4 goes into 5 one time. So I have 1 left over. I'm going to bring down the 4, and 4 goes into 14 3 times, and that's going to be 12. Subtract that from 14, and we get 2. Bring down the next number, which is 3. And 4 goes into 23. Again, I know the multiples of 4 pretty well. The quotient, not so much. But again, I think it's just because I already know it's not important. So my brain's already removing that task to save space, because my brain gets tired too. But again, the important part is this part here. That's our power. Well, I shouldn't say that's our power, but that's the equivalent. That's what it would come out to be anyway. And I'll explain it with this next example, because this next example, exercise number 6, is pretty easy. You'll be able to see why it works, like just by looking at it. So for this one here, we might need the chart, which I think it's negative. So I to the 3rd is negative I. All right, I just had to make sure. I don't want to put the wrong thing in there. And there we go. That's it for that one. Now with this one, number 6, I'm going to do that one a little bit differently. We could divide it. 9 divided by 4 is 2. But then if we count by 4, we get to 8, and we have 1 left over. So you kind of already know what this is going to be. But I'm going to show you each part step by step. So I'm going to put it into powers of 4, because again, every 4 times it repeats itself. So here I have 4 power, which is 8 power. But I need one more here. Now we know from the chart, I to the 4 power is equivalent to 1. So if I evaluate I to the 4 power, I get 1 times I. And we also know from the properties of numbers that 1 times anything is not going to change anything. It's just going to stay whatever number it was, what we call the identity property. So timesing something by 1 doesn't affect the value of the number. So in this case here, I end up with just I. Well, it would be I to the 1 power, but we don't really need the 1 power. And plus that, since I wrote everything out, I can easily see that there's only 1 I right there. So again, when you evaluate it, it's always going to just come out to be 1 every 4 times. All right, let's go ahead and try this one. Now this one's a little bit of a tricky one because I did it this morning and I had some people looking at it like, why? Why did it, what happened to that first number? So 4 goes into 8 exactly 2 times. Now this doesn't really happen in division all that much because if I were to put the next number down here, it would be 8, which would give me 0. And I think even I've had some college students that think that when you get 0 down here, that's the end of it. So 4 dividing into 834 only fits in there 2 times. No, I don't know why that happens, but it is something that I noticed that happens with people. So I didn't put anything in there below that. 4 does not fit into 3, so I'm going to put 0 there, but I don't ignore the 3. I combine it with the 4, so I treat it like it's 34 now. And 34 fits into 34 about 8 times. And counting by 4, I get to 32, which is my number down here. Subtract that. And again, it's 208, but we're really focused on the remainder. That's the part that it becomes equivalent to. So in this case, I get I squared, which is going to be, and again, if you're not sure, always go back to the chart. I squared is -1. So answer for this one is -1. All right, luckily for this one, we have a much smaller number. 4 divided by 55. All right, so 4 goes into 5 1 time. 5 minus 4 is 1, and bring this down so it becomes 15. And 15 minus 12, oh yeah, I forgot I almost put it up here. But again, this part, we don't care about that. And anytime you're doing division, yes, that is the part you are most concerned with, but not for this one here. So I end up with 3 left over. And 3, I to the 3 comes out to about, so again, if you don't have the chart, you can also just sort of, oh, well, I don't need the chart or to figure it out because I also have an I to the 3 right here. And again, there's only 4 possibilities that it can be. It can either be I, -1, -I, or +1. Those are the only options that it can be. Okay, last slide. All right, 910. So we just have to divide 910 by 4 to see what power it's equivalent to. 910. Now there's also some other tricks you can do to divide by 4 faster, but that would be a whole different lesson on its own. But again, as long as you remember your long division rules, then it wouldn't be all that different. So I get 1 left over, bring that down, and I have 8 here, so that's going to be 2. 11 minus 8. 11 minus 8 is going to be 3. Bring this down. Don't forget, just because you see a 0 doesn't mean it's over. So in this case, I know it's going to be 28, which is going to be 7 up here. But again, we don't care about this up here today. It's kind of like that one episode of SpongeBob. It's one of the classic episodes. So in this episode of SpongeBob, him and Patrick buy a large television set so that they can get the box. They wanted that large box so they could play inside of it. It's kind of like that. So even though you're doing division, that's usually what you're looking for, just like you'd normally be looking for a television. But in this case, we want the box. So since we get a remainder of 2.
Teachers, please have your packets ready for week 3 out on the table. We already have parents coming in asking for packets. And when I go to the tables, there's none. Please make your packets available on the tables. They should have been due at noon. Thank you.
Okay, I was saying that at the beginning of this, right before we started the lesson, I said, oh boy, it's been a really busy day just because of everything that's been happening here. And you can tell right now there's a bit of that in the air going around here. So I went ahead and used that time and I expanded I to the 5 all the way out. So what I to the 5 means is root negative 1 times root negative 1 times root negative 1 times root negative 1 times root negative 1. So I have a lot of stuff going on there.
Mr. Nez, is it root negative 1?
Yeah.
Is it root
Yeah.
positive?
Positive?
It's I to the 5th, 5 to the I to the 5 power.
In this case, I'm not using this method here. I'm going to write the whole thing out because this is a small enough number to where sometimes I do get that question of like, okay, well, I know how to do it, but I don't know why it's done that way, or I don't know how it works. And some students are like that. They're pretty curious. Vast majority of them, they want to know just enough information to do the work because for them, finishing the work is what's important. But for other students, once they fully understand the assignment and they complete it, they kind of want to know why they're doing something. So that's kind of what I always try to do here is to explain how and why something works and how you do it, why you do it, how it works, and why it works. All right, so I'm going to use a multiple tree like this, root negative 1 times root negative 1. So again, if you have 2 multiplied together, that releases the radical. So now I only have negative 1. But by that same definition here, if I multiply the same thing, I should get the same answer, same result. So negative 1 times negative 1, and I haven't done anything to this one, so it stays. So I end up with negative 1 times negative 1, which, well, negative times a negative is positive. So positive 1 times root negative 1. 1 times anything does not change the value. So it stays as the square root of negative 1. Which is the definition of I. I is the square root of negative 1. Because again, we have to come up with a way of working around having negatives in the roots, because that's not something that can happen, but sometimes you can change it later on down the road to make it work. Okay, now this shows you what you're actually doing. But the problem is when we are writing the whole thing out, if I had to write out the square root of -1 910 times, that would take a very long time. And even I have better things to do, like pet an animal. I would never have time to pet animals if I had to keep doing all of this stuff here. So that's why we have the shortcut.
Call to all teachers, your package should have been on the table by 12 this afternoon. Please adhere to deadlines. Thank you very much.
I had to really scramble and make sure mine was all together by the deadline. I had to call my first hour a little bit short so I could wait in line at the copy machine, which there was a big line at the copy machine, and I had trouble printing out the thing because the page would be a little bit wrong, so I'd have to go back, print it again. But by that time, someone's already printing 100 copies of something. But I got mine done. I had to stay in for lunch to get it done. All right, so now this one's kind of an obvious one again, because if I asked somebody, like if I was just walking down the street and I asked some random person, is 32 divisible by 4? They'd probably sit there, roll their eye a bit. Yeah, it is. So that means there's no remainder. And again, anything to the 0 power, even if it's I, or if it's negative, anything, fractions, negatives, anything you can think of. If it's to the 0 power, it always comes out as 1. It's just the law that happens. All right. It's just the law of the way things go. That one wasn't that bad. Let's go ahead and do this one here. So 618. Divide that by 4. All right, now start dividing. So 4 goes into 6 one time. 6 minus 4 is 2. Bring that down. And going by multiples of 4, I'm going to go ahead and, I know it's going to fit in there 5 times, which is 4 times 5 is going to be 20. And I'm doing this one a little bit differently because I keep telling people that these top numbers are not that important. So I'm just doing it without the top numbers. Okay, I don't need no top numbers telling me what to do this time. All right, fine. If you really, really want to, you can go ahead and put that in there. 4 goes into 6 one time, goes in there 5 times, and it goes in here 4 times. But again, we don't want the television today, we want the box. So I squared is root negative I times root negative I, which is just going to be -1. Or again, with this assignment, there's only going to be a few of them. So I'm guessing after you do enough of them to where you get all 4 of them, you can just look in your own homework and see which one comes out to what. Okay, so that's it for today. It looks like there's no more exercises after this. We would normally have a little bit of a wind down and a closure, but kind of tough when I don't have a whole lot of students and I don't have a whole lot of way of responding. I think some students don't have microphones, and I'm not going to hold it against them if they don't. So I think that's it for today. Let me go ahead and go back to the, go back to the other screen. Oh, okay. All right, well, again, thank everyone for showing up. I'm glad you are all here. It lets me know how you feel about school and all that stuff. If you have, as always, if you have any questions, I'll be around for the next few minutes to answer anything you have, because we still have a few minutes of class left. So if you have any questions, I'll be around. If not, that will be it for today. Bye-bye now.
Thank you, Mr. Ness.